Okay, just so you're, if you've missed the last couple days, which is just a couple of people probably, we want to look at rational functions. Rational functions are polynomials stacked on top of each other. So you create a fraction of polynomials. The things we want to know about them are the x-intercepts, the y-intercepts, the vertical asymptote, the horizontal asymptote, and a thing called the slant asymptote that if that exists, we're going to find that. And we'll be looking at those individually on the next few slides. The domain of a rational function, first you consider it's all numbers, but then you realize that the denominator of that rational function can never be zero. And so we're concerned always with what makes this equal 0. Well, in this case, the number 7, not 10, I don't know what that said. The number 7 is a 0, okay? And so we want the domain to be all numbers except 7. Now, you could say that all numbers except 7, writing it out in words. You could say negative infinity to 7, 7 to infinity, union together. I kind of like the shortest way possible, where we just say all numbers except 7. And if we say x is not 7, that is the domain of this function. Okay, the vertical asymptote of a rational function is where the domain does not exist. So right here we realized that what made the bottom turn to 0 was 7. And at x equals 7, there is an interesting idea that the graph 1, 2, 3, 4, 5, 6, 7, we'll even put 8, the graph at 7 will get closer and closer and closer and closer to that line. So perhaps, and don't take this for the exact graph because I have not graphed it on my calculator, but perhaps the graph does this, and perhaps the graph does this, where it gets closer and closer to that vertical asymptote. But anyway, what we're asked here is the vertical asymptote, and that happens where the domain doesn't exist. So the vertical asymptote is just simply x equals 7. The x-intercepts of a graph, what we learned real early in the course of pre-calculus is that you find x-intercepts by letting y be 0. So if we let y be 0 in this problem, we create this situation, where we will want to multiply both sides by the denominator x minus 7. And what we realize is that anything times 0 is still 0. And when you multiply by the thing you're dividing by, oh, that just cancels. So you're left with x plus 1 equals 0. If I subtract 1 and I subtract 1, x is equal to a negative 1. Now, an intercept is a point. So let's put that over here as an ordered pair. The place it hits the x-axis is negative 1 comma 0. That's the x-intercept. Y-intercept of a graph, the y-intercept of a rational function is really incredibly easy because, as we stated the very first day of pre-calculus, you let x be 0 and see what you get. So if I let x be 0, this becomes a 0 and this becomes a 0, and therefore I have 0 plus 1 is 1, and 0 minus 7 is negative 7. So the y-intercept is the point where x is 0, and the y-intercept is negative 1/7. Now sometimes there are horizontal asymptotes on a graph. And a horizontal asymptote is kind of like a vertical asymptote, except it runs horizontally, and horizontal asymptotes can be crossed. So your graph might go through the horizontal asymptote. That is never true about a vertical asymptote, though. The graph doesn't exist there because the domain says it can't. Okay? But anyway, on the horizontal asymptote, we're looking at one of three conditions. I reference these probably not quite like your book, but when the degree of the top is bigger than the degree of the bottom, I reference that as top-heavy. And in a case where the graph is top-heavy, or the function is top-heavy, the horizontal asymptote doesn't exist, so we would just say there isn't one. In a case where it's bottom-heavy, that is where the degree of the bottom polynomial is bigger than the degree of the top polynomial, I reference that as bottom-heavy. The horizontal asymptote is always, always, always found at y equals 0. And the case where the degree of the top is exactly the same as the degree of the bottom, I reference that as a balanced situation. You peel the numbers right off the front, the coefficients off the front. So the 1 in front of the x on top over the 1 in front of the x on the bottom, the horizontal asymptote is at y equals 1 over 1, or just 1. So y equals 1 is this one. So under those three conditions, you can find the horizontal asymptote of a rational function really quickly just by looking. And so we'll do some more of that in the examples to follow. Okay, let's start with this example and kind of run through all of these things all at once. So let's start with domain. What is the domain? The domain are all the numbers we're allowed to use to insert into an equation, okay? And we would concern ourselves with any time the bottom would equal 0. So the number that makes the bottom equal 0 is 4. So the domain is all numbers except 4. The vertical asymptote, let's do this one next. The vertical asymptote is where the domain doesn't exist. So since the domain doesn't exist at 4, a vertical asymptote will actually happen at 4. The horizontal asymptote is dependent upon being top heavy, bottom heavy, or balanced. And since we look at these degrees of the top and degrees of the bottom being the same, I'd consider that to be balanced. We'll peel the number right off the front, the coefficients, and therefore we have y equals 1. 1 over 1, which is 1. The x-intercepts, we let the y part of the problem equal 0 and solve. So I would multiply both sides by x minus 4. And x minus 4 divided by x minus 4 would cancel. Anything times 0 is still 0, so 0 will equal x plus 1. And now we would just simply subtract 1 to get x by itself, and x is negative 1. However, we want to write intercepts as points, so the ordered pair for the x-intercept is negative 1, and the y is 0. And the y-intercept you get by letting x be 0, so the y-intercept would be 0 plus 1, 0 minus 4. It would just simply be negative 1/4. And there are all the components we'd want to know about this rational function. Okay, just kind of showing or talking about this one here as it's already all been done here. We would want to consider the domain to be what makes the bottom turn to 0. So we might consider factoring that as the difference of squares, so x and 3 and 3, and then 1 positive and 1 negative will give us x squared minus 9. So what makes that 0 is negative 3 and positive 3. We do not want to have those numbers in our domain, and so the domain is not 3 and not negative 3. The vertical asymptotes happen where the domain doesn't exist, so the vertical asymptotes are indeed at x equals 3 and x equals negative 3. And it is a bottom-heavy situation since the exponent on the bottom is 2 and the degree on the top is 1. It is bottom-heavy. And under all bottom-heavy conditions, the horizontal asymptote is at y equals 0. I'm going to look at this one problem here and just realize that it's a little bit tricky. Maybe you think x squared plus 9 factors, but it doesn't. Maybe you think 3 and negative 3 make the bottom turn to 0, but they don't, because 3 squared is 9, and 9 plus 9 is not 0. And negative 3 squared is also 9, and 9 plus 9 is not 0. So just be careful when you consider the domain of that the domain is all numbers. You will never be able to make that denominator end up at 0 no matter how hard you try. And the vertical asymptotes do not exist because there is no concern of the denominator ever being 0. And the horizontal asymptote falls under the condition of being bottom heavy, so it is y equals 0.